This is a lecture in engineering, computer science, computer architecture course, computer architecture and high-tech fundamentals, engineering/CS 230. I'm Professor Joseph Wunderlich. This is one example, a floating point. You may or may not have seen previous examples. Typically in this course, you should have seen previous examples at the end of the number representation lecture, which you should go back to after looking at this and work through all of those. So this is a conversion or a representation in binary floating point in the computer. You see all these bits at the end of the problem where you're taking a decimal number and you're putting it into binary. So in this example, we're given 0.75 in decimal. And the first thing you want to do is get it into some form of binary. So for this particular example, you're not always going to do this kind of thing, but you see 0.75 is the same as 3/4, which is also the same as 3 over 2 squared. And there's the 2 that you need. Then in this example, it's a little different than most. You're kind of leaving the numerator, the denominator in base 10. The numerator is going to base 2, which is a little unusual. But you can see the reasoning here, hopefully. 1 in binary is the 3 in the numerator. The denominator is 2 to the 2, which will turn out to be the power of 2 that you're going to need in your representation, your scientific notation, binary floating point representation. And so now they're saying 1 in binary divided by 2 to the 2 is the same as 0.11. And the way you get that is you say the 1 divided by 2 to the 2 is the same as 1 times 2 to the negative 2. And then you move the decimal point of the 1, which is 1.0, over to the left 2 points. That means 2 spots. That means you need to reduce the exponent of the 2 by 2. So then you end up with 2 to the 0, which is the same as 1, and that's why you see no power of 2 in that. But now you're going to reintroduce that back in by just the next line down there. You see, let's say 0.11 times 2 to the 2, or times 2 to the 0. So there it is again. And that is getting close to what we need to stuff it into our bits. So we still need to normalize it. Normalizing means to get it in some form of 1 point something. And so you always want that 1 there. And then it's going to be just implied. And you'll see in a second what I mean by that. So we move over the bits now to the right. You got 0.11 times 2 to the 0. We move the bits over the bit over 1. So you get 1.1 instead of 0.11. And that means you're making the number bigger right there, that 1.1 part. And that means you got to reduce the exponent on the 2 by -1, or by -1, so 0 minus 1 is -1. So now you have 1.1 times 2 to the -1. The whole thing's negative. Now this is the normalized form. Now you're ready to stuff it into the equation that represents how the bits lay out. So here's the equation now. Now this is also a negative number, so that you have this equation, -1 to the s times 1 plus a significant times 2 to the exponent minus 127. There's a formula up there. So that can throw you off. So we look at our normalized representation of -1.1 times 2 to the -1. It's a negative, so the s needs to be 1. And you look at how does that work? Well, you have -1 raised to the s power. If the s equals 1, then the -1 stays. It's a negative number. And that's what you put down in the representation, a 1 in that bit field for the s. If it's a positive number, you put a 0 there. The s equals 0, which -1 to the 0 just makes 1. Anything raised to the 0 power is a 1, whether it's negative or not. So that's how that works. Then the times 1 plus the significant. So the 1 in this normalized representation, since you always are putting it in that form before you stuff it in the bits, it's always implied. It's in the machine. The machine knows it's there. It's in part of the computations. It knows it's there. But you don't need to show it because it's just implied. It's implied. It's a little confusing. You don't see it in the bits down below. It is implied. That 1 to the left of the decimal point is implied. Then you have the significand, also called the mantissa. It's the same thing. significand and mantissa, and we use those synonymously. And that's all the bits, the binary bits to the right side of the decimal point. And so in this case, we have negative 1.1 times 2 to the negative 1, so it's just 0.1. And so that 1 of the 0.1 goes down into the bit fields, bit number 22 you see down there. And you say, what are all those zeros? Well, it's a 32-bit representation, so that's just what the remaining precision is. You're not using it in this case, but because it's a single precision floating point, those bits are there. They're just there. Then perhaps the trickiest part is this exponent. So we started with negative 1.1 times 2 to the negative 1. And now you're saying, well, negative 1's the exponent. Well, it's not what goes into the field of bits, the 8 bits below. You see that E down there. There's 8 bits. That's not what goes in there. You take that negative 1 and you set it equal to this exponent minus 126. What you're trying to do is you're trying to get a negative 1 in the representation, but you put in this formula because of minus 127 so that this representation can represent a spread of numbers. So if you had a 0 in the exponent, then that's negative 127, that's minus 127, that's to get to 0 you put 127, and then if you want a bigger thing, you max out, or if you, like, for example, you had a 0 in the exponent field and the 8 bits, then that would be 0 minus 127. That means you had in your original normalized thing a minus negative 127, so you had a really small number. So what it's giving you is a flexibility to do a range of numbers, and this will become clear when you go back and do other examples. In this course, you want to be doing all the examples in the homework problem solution you see at the end of the number representation lecture. If you're seeing it in other places as a review, it wouldn't hurt to go into some other places and try some examples. Just make up some numbers and see what you have to do. What you see in the bottom here is double precision, and everything's exactly the same as the single precision, except instead of saying minus 127, you're doing minus 1023, and that's to give you a larger range of numbers. 2 to a bigger number to 2 to the smaller number. Bigger number range in magnitude, and then in both positive and negative magnitude, and then you see in the you have 20 bits plus 32 bits in the mantissa field. You have all those bottom bits there, a lot of bits that allow you to have a great deal of precision. So you're talking about magnitudes ranging positive, large negative, and also precision.